All right, our first speaker will be Peter Russell from Missouri Theta, and he will explain to us circular projection of ellipsoids. So we'll turn over to Peter.
Yep. So I'm Peter. So about a year ago, I did somewhat the same talk, but I've got more to talk about this time, and I've got toys. So let's go ahead and get into it. Or not. Okay, there it is. Okay, so an ellipsoid looks like this, probably from top three. So it's an ellipse in all of its kind of main cross sections, but it's basically 3D. So it has this particular form when you kind of write it down, and where A, B, and C are kind of the main axes. So we kind of call this kind of distance 2A and 2C and 2B. So that's kind of some background on that. So the question we're going to ask is, if we take kind of a light source at the top and we project this shape down to the XY plane, is it always possible to rotate it in such a way where the shadow that's projected is a perfect square? So if you hand me any ellipsoid of any dimension, will I always be able to project it or rotate it in such a way with projection it's a circle? And then if that is the case, if I can always do that, what are all the possible ways I can do that? So that's kind of the problem that we're going to be working on. So just as a kind of template of what we're going to be doing here, we're going to define some assumptions, because assumptions are always helpful. It's going to help us solve some problems. We're going to kind of decide on a particular rotation that we're going to send the ellipsoid through. That's going to kind of give us our best chance of trying to find a circle. And we're kind of talk about that in a little bit. We're then going to show that all of the projections under this particular rotation they're all ellipses. And using the intermediate value theorem, we can basically show that there must be some angle through that rotation. And then we're actually going to show that this size circle is the only size circle you can possibly make using that particular ellipsoid. So yeah, that's kind of our goal. So our assumptions. The first one's pretty simple. We're just going to project onto the XY plane, just because we can always rotate our coordinate system, to match anything we want to do. So we're just going to keep it simple and do the XY plane. We're also going to make sure that the ellipsoid's centered at the origin, because if it's not, we can just move it. And it's going to be rotated in such a way where the kind of X direction is A, the Y direction is B, and the Z direction is C, where A is less than B is less. Okay, so we're going to take our ellipsoid and we're going to rotate it kind of in this direction, because kind of around the y-axis, because if we have when we have whatever numbers in the middle and we rotate it, we're starting with something that's longer than B, and ending at something that's shorter than B. And so we can imagine that if all of the shadows are ellipses, we know that somewhere in between there has to have some dimension this direction that's the same as the dimension this direction, because through the rotation, this dimension doesn't change. So that's the idea. So the only kind of trick we need at this point is to show that along this rotation, every single rotation or every projection we have is always going to be an ellipse. That's our goal here. So in order to do that, we're going to take like an arbitrary point, an XZ. Since we're rotating around the y-axis, we're just going to forget about the y-coordinate for now, and we're going to look at a point X comma Z. We could do this with like a matrix multiplication, but I think it's more fun to do it with polar coordinates. So we're going to kind of translate this polar form. And of course, we have R is equal to the X squared plus the Z squared. And we can call phi equal to, I guess, these three things. Gonna kind of deal a little bit loosey with it, but so we can add on a rotated theta in this polar form, and convert back to rectangular. And we're left with this R times the cosine of phi times theta times R times sine of phi times theta. And we can get our arms deep into some algebra, where we can use our angle addition identities from trigonometry to expand this into r times cosine of phi times the cosine of theta minus sine of phi times the sine of theta, comma r times the sine of phi times the cosine of theta plus cosine of phi times the sine of theta. Bit of a mouthful. We can use basically what the cosine of phi, the sine of phi are equal to, and kind of just substitute those in. And we're left with this kind of third row here. Just the r times the x over r times the cosine of theta minus z over r times the sine of theta, comma r times z over r times the cosine of theta plus x over r times the sine of theta. And nicely, the r's all cancel out, so we don't have to worry about the big old square root. And we're just left with this x times the cosine of theta minus z times the sine of theta, comma z times the cosine of theta plus the x times sine of theta. So we have this nice kind of rotation of our point around the y-axis by theta. So we can go ahead and plug this right into our ellipsoid. And technically, this is going to be the set of points so that when they're rotated, they give you your kind of formula, the ellipsoid. So this is actually going to be the ellipsoid rotated in the other direction. But because this rotation essentially achieves the same shape as rotating the other direction, it's fine. We can just work it like this. So just plug it right in. And this is our equation of our ellipsoid rotated around that particular axis that we're going to be rotating around by theta. So the idea here is that we want to kind of have the boundary of our shadow. Those points that form the boundary are going to be exactly the points where along the ellipsoid, where the tangent plane is exactly vertical. And so we can use the gradient in order to find those points, because we know that the gradient is always kind of normal to the shape that we're looking at. So we're just going to find the gradient of this shape and set the z component of the normal vector equal to 0. So that's the idea that we're going to go here. So all the points that we're looking at are going to satisfy the gradient is equal, or the z component of the gradient is equal to 0, and the function of that point is equal to 1. So doing that, we can do a little bit of algebra, and we find the z component of the gradient just by taking the z partial derivative of our kind of equation of the function, which gives us this -2 times x times cosine of theta minus z sine theta times the sine theta over a squared plus 2 times z cosine theta plus x sine theta times cosine theta all over c squared, and that's equal to 0. Because we want that z component to be 0 for the tangent plane to be vertical. So we can do a bit of algebra here. We can divide both sides by kind of our 2 to get rid of that constant, and then multiply both sides of the equation by a squared times c squared, which is legal because we made our assumption that a and c are both positive, so we're good in that regard. Which brings us to the a squared times z times cosine squared theta plus a squared x sine theta times cosine of theta minus c squared x sine theta cosine theta plus c squared z sine squared theta, and all that is equal to 0. So from there, we can move everything that's got a z in it, or to one side of the equation, everything that doesn't have a z in it to the other side of the equation, and then factor out a z on the left-hand side and divide by everything else. And you can see that that thing that we're dividing by is positive, so we're not dividing by 0. So this is fine. So we're just left with z is equal to x times the sine theta cosine theta times c squared minus a squared all over a squared times the cosine squared theta plus c squared sine squared theta. So we can do a nice little simplification here, because we know that theta, a, b, and c are all constants. So we know that most of this is just a constant, and I don't want to have to write all of that out. So we're just going to call all of that out. and make the little substitution. And we're just going to call x equal to x times some constant L, where L is that nasty thing. So we're going to substitute our z equals x times L right back into our equation of our ellipsoid, rotated ellipsoid specifically, where we end up with our x times cosine theta minus x times L times sine theta squared all over a squared plus our y squared over b squared plus x times L times the cosine of theta plus x sine theta squared all over c squared is equal to 1. We can factor out an x from each of these two sides and square it so that we can kind of pull it out of the parentheses of the square, which gives us our second line. And then we can combine the first term and the third term by finding like terms and just adding them together like fractions, where we end up with our x squared times c squared times the cosine of theta minus L times the sine of theta squared plus x squared times a squared times L times the cosine of theta plus sine theta squared all over a squared times c squared plus y squared over b squared. That's equal to so from there we can just pull out our x and move everything, or sorry, x squared, and move everything that's in that term that's not the x squared into the denominator. And we've got this nice thing on the bottom row here, which this bottom kind of the denominator of the x squared term, it's just got constants in it. So this is an ellipse. It's a nasty looking ellipse, but it's an ellipse. So we have shown that every rotation that we can do along that special axis is an ellipse. So from that, we know that as we're rotating through that axis around this y-axis, we know that there is a time where this kind of forward dimension here is exactly equal to this side dimension here. And the only ellipse that has its kind of two axes equal to each other is a circle. So we don't know what the exact value of our theta here is, but we know it has to exist. We know that there has to be some rotation around that axis that gives you a circle. Yeah, so I kind of promised earlier, I kind of give a little spoiler, I guess, that this was the only size circle that you could make, which is kind of surprising, I suppose. And the way we're going to do that is we're going to first show that the circle can't have a radius greater than b. So if we take our ellipsoid and we kind of imagine encasing it inside of a cylinder, kind of height 2a and of a diameter of 2b. So it kind of barely encases the ellipsoid. And we kind of imagine rotating this ellipsoid, this cylinder. We know that the encasing of the cylinder, the shadow of that cylinder has to be kind of outside of the shadow of the ellipsoid. You know that this shadow is going to sit inside of that cylinder shadow. So anything that we kind of say about the size of the cylinder, we know that this has to be smaller. And if we have that cylinder that has a radius of b, we know that we're always going to kind of have two parallel lines in the shadow that are a distance of 2b apart. And so we know that there's going to be some radius through that shape that's a distance of 2b apart. And because we know that the shadow of the ellipse has to sit inside of that, we know that the shadow of the ellipsoid can't have a radius greater than 2b because the cylinder doesn't have a radius greater than 2b, or a diameter of greater than 2b. So now we can show that the circle can't have a radius of less than b. The way we're going to do that is we're going to kind of imagine taking this slice out of the ellipsoid, this kind of slice. We're going to imagine having kind of a clear boundary where the ellipsoid is. So the shadow of this shape has to fall inside of the shadow of this shape. kind of in the same way that this fell inside the shadow of the cylinder. So if we think about what happens to this projection, we can answer some questions about how that's this one. So if we imagine any rotation that we rotate this thing through, we can imagine slicing it with the XY plane. So any kind of orientation we put this in, we're slicing it through the center by the XY plane. Since we're projecting onto the XY plane, kind of looking at a distance here. And if we look at this, any line that goes through the center on an ellipse has to be greater than or equal to the length of this kind of line axis. Because this is the shortest distance you've got. And if you start moving your points outwards, you're getting a greater distance. So we know that there is at least one line, one diameter, you could say, of the ellipsoid shadow that is greater than, potentially greater than or equal to 2D. So we know that if we have a circle, that it both has to have it can't have a radius greater than B, and it can't have a radius of less than B. So we know that the radius has to have a exact radius equal to the kind of middle distance of the ellipsoid. So that's that. So kind of things that we didn't work on is we didn't find the kind of an elegant solution for the exact value of theta. I kind of let my calculator run wild, and it was able to find something, but we weren't able to actually figure out how to work it out. So that could be a fun puzzle. And then another thing is you can go, okay, well, what about like kind of maybe a 4-dimensional ellipsoid kind of shape and its projection into 3D space? You can always find one that, find a projection that's always a sphere, or maybe even more general than that. So that could be kind of a fun experiment to kind of think about. Yeah, any questions? Yes.
3 minutes of questions.
Have you considered using a point source instead of a cylinder to move your shadow?
I thought about it, but we didn't consider it for this particular presentation. Yeah.
It seems that would be interesting because you'd be sort of fitting inside a cone instead of inside a.
Yeah. It's definitely would be very interesting. Yeah.
Let's thank our speaker.